Hello, my name is Greg Freeberry, and for the final research project of the clustering algorithms class, I decided to do my research on doing image segmentation using PSOQI, which stands for Particle Swarm Optimization with Quantum Infusion. Now, image segmentation is a pretty popular part of clustering. It's pretty popular amongst a lot of people, and it's a popular problem to solve. So I thought it'd be kind of cool if I could use this PSO algorithm to do image segmentation. Now, I got this benchmark problem from the UCI repository, and unfortunately they didn't provide the actual image to me, but they did tell you what the image is divided into, and it's divided into 7 different segments, which include brick face, sky, window, foliage, path, grass, and cement. So you can imagine it's, a brick building somewhere in a wooded area with grassy yard and a path. And the goal is to identify these separate segments, or these separate classifications into segments of the image based on these 10 attributes, which is mostly just color information such as hue, saturation, intensity, RGB values, just color stuff like that. And what we use to segment this image is a particle swarm optimization algorithm. Now what particle swarm optimization is, the basic one, is just a global swarm algorithm which uses multiple individual particles in parallel to explore the search space for the optimal solution. Now what this basically means is that each particle is in the search space of this 10-dimensional search space, because each attribute represents a dimension. So these particles are flying around in this search space and they're trying to find the best solution. Now the particle utilizes its own momentum along with trying to move towards its own personal best, and then also towards the overall best, the best solution that has been found so far by the overall PSO algorithm. This diagram should help explain it better. Here's your original position, and here's your final position. You have your momentum term, which I said was just whatever direction the particle was already moving, it has a portion of that included. Then next is the cognitive term. It starts moving towards that particle's own personal best, its own optimal solution that it had found up to that point. And then also the social term, which was the overall best solution found by the entire algorithm. So each particle includes all these 3 terms as it moves about this search space. And here's the velocity update. As you can see, it might be hard to see, but you can look at it later. And then QPSO is Quantum Particle Swarm Optimization. This was created by Soon in 2004, and it's based in quantum mechanics, which means that it's probabilistic instead of deterministic, which means basically that the position and velocity cannot be known simultaneously. So what QPSO does is it does away with the velocity equation that standard PSO employs, and it derives its position update equation based on the Schrödinger equation, which is the governing equation for all quantum mechanics. And I wish I could go into more detail about it, but you can read more about QPSO if it interests you. But here is the particle update for QPSO. First you have this P, which is just a local attractor point that's created by, as you go through this QPSO algorithm. Then the M best is the mean best particle, which means you add up for every particle the one dimension, each dimension, and then you divide each dimension by how many particles you have. So each particle, whatever value they have for that particular dimension, you add all those up, you divide, and then that would give you the mean for each dimension. And then this U is just a random number between 0 and 1. So that all that leaves left is the beta, which is called the creativity coefficient, and you can scale this up or down to decide how much effect you want the QPSO to have. Now, what PSOQI is, when we infuse the quantum into the PSO, what we're doing is particle swarm optimization, just the standard one, has very fast convergence speed, whereas QPSO gives more quality results, but has slower convergence speed. So what we do is we just go through the entire regular PSO algorithm and do all the updates necessary. And then once the PSO is finished, we select one particle from that and then perform the QPSO and produce offspring with this QPSO algorithm. Then we compare this offspring to the personal best, the P best of the particle, and the G best, which is the overall best. And if these offspring from the QPSO have better fitness than the P best or the G best, then the offspring replace those. Otherwise, it's discarded. So in this way, we can kind of preserve the convergence speed of the standard PSO while infusing a little better quality results by putting the quantum part in there as well.